Okay, so good morning, everyone, and thanks, organizer and ICTS for hosting this nice meeting. And in last few days, we have listened a lot of talks on cold atoms and their applications, quantum simulation, quantum technology. I will a little bit touch about a different kind of cold atom, and that is observed as a form of quantum droplet 10 years back. And we have performed some mean field simulation to analyze the structure and dynamics of this quantum droplet and how we can manipulate it using some spin orbit coupling, light matter interaction. And then I will discuss about some of our recent result where we are trying to address the long-standing problem about the classical turbulence, that how it arises and how the energy cascade gets controlled in the context of quantum turbulence that is being generated in this quantum droplet. And today I'll try to basically show some of our the recent result where by tuning the ground state of the quantum droplet, we can achieve towards the classical turbulence energy cascade. And also we can get the quantum cascade as well as classical cascade in some of the regimes. So I will try to basically go in the direction. And this already has been introduced by Professor Adhikari quite nicely about the mean field, that kind of thing where you're using for Bose-Einstein condensate. As we cool it down, then at zero temperature, all the particle lose its identity and we can represent their behavior with a single macroscopic wave function. And it started all with the Bose-Einstein, and then it took 70 years to observe this thing, and many pioneer people are in this conference. Dan Stamper-Kuhn is here. So I just wanted to basically take you this 100 years of BEC, and throughout the way, it has seen many of the development in cold atom field. So it started with the quest of low temperature phenomena, what was observed in liquid helium, and then in the beginning of quantum mechanics, it started with the Bose-Einstein theory. And then the quest of getting this thing as an experiment, with several kind of the other theory was developed in liquid helium-4. Then this in superconductor BCS theory came, and Landau got the Nobel Prize in 1962 to describe the superfluidity in liquid helium. Then there was a Moser laser that got the Nobel Prize. And then you can see that throughout this journey of the 100 years, time to time, it has brought the Nobel Prize in this field in different contexts, sometimes in the like a technological context like Josephson superconducting circuit. Then in this time for the technique to develop this the low temperature to get this cold atom, coherent energy and group. And then in 2001, finally, this much way it has to travel to get the Nobel Prize in BEC. And after that, it didn't stop in that the phase only. Then people basically use it for topological matters and so on. And now at this era, people are looking for some sort of technology and some other form of matter using this cold atom through which we can do some exciting physics as well as technology. So the journey is continuing, and that we have learned from this conference. And my group in IIT Guwahati is involved in addressing several aspects of this Bose-Einstein condensate. So Swaroop is here. He basically did his PhD on Anderson localization in Bose-Einstein condensate. There we basically describe many of the localization behavior. And then we did some work on spin orbit coupled quantum droplet. Some work we have just completed on the synthetic, this rotating BEC in presence of synthetic gas field, where we study different kind of excitation that vortex lattice can have. And then we have some work on quantum turbulence in quantum droplet. And also our group is now actively working on some of the nonlinear patterns that we can get in these different phases of condensate. Some work on quasi-periodic excitation in condensate. And with Professor Muruganandan, we have some work where we have used this self-gravitating BEC to address many of the astrophysical phenomena like glitches in neutron star and dark matter. And in the technological aspect, we just started some work where we have proposed some theoretical model to get the circuit for the neutral atom, and we can detect it using the condensate cavity coupling. This work Nalini Kanta will be talking in the tomorrow lecture. So today I'll be focusing about two aspects of quantum droplet. One, how can we tune this different ground state of the quantum droplet using light matter interaction, especially the spin orbit coupling. And then I will discuss about the quantum turbulence. So this quantum droplet in binary system started with the experiment by Letizia Tarwell group. And here what we see that how with the phase-back resonance, we can tune this scattering length. So this corresponds to the scattering length between the down-down hyperfine states, and this corresponds to the scattering length between the up-up hyperfine states, and this with the up-down. So what we see here that delta A, which is the difference between this intraspecies and interspecies interaction. If it is negative, then we basically, if we release the trap, this condensate doesn't get dispersed like when we have delta A greater than 0, when it behaves like a gas. But here we get some bound state and it remains for some time. And that is the discovery of liquid kind of behavior in this Bose-Einstein condensation. So, and this is the thing one can get that if the interaction is totally attractive, then this condensate will get collapsed. So, to understand the theory, we have to go beyond mean field theory, as Professor Adhikari mentioned in his talk. But here I just want to give a brief introduction about this beyond mean field theory, how it is useful for binary condensate. So one can get an idea by taking a single component, and this is the way mean field energy goes. So here what we see that if G is greater than 0, then it will behave like a gas. It will keep on expanding. If it is less than 0, then it will get collapsed. So we cannot get this liquid kind of behavior or bound state for the single component. But mean field theory is here, that is coming with the one contribution, and then we have beyond mean field term. So here what we find that this particular term is very small. That's why this beyond mean field term didn't appear for the single component gas. And here we have shown that how the energy goes. So when we have a different sort of interaction. But once we consider the binary gas, then we have the intraspecies interaction and interspecies interaction. So this is a condition through which we get the miscible gas. This is a condition we get immiscible gas. And in this condition, we have the unstable regime. So in mean field theory predicts that this region is unstable one. But in beyond mean field term, what happens that we have the next order term that becomes dominating. So this one is mean field term is attractive, and this one will become repulsive. And then we have this compensation between the beyond mean field term, which is positive, and mean field term, which is negative. And at a particular density, we have the formation of bound state that we are calling it liquid droplet state. So, so in this case, I'll be talking about this structure and the dynamics of this quantum droplet in presence of spin orbit coupling. And there I will show that how can we tune different ground state of the liquid droplet. So this is the beyond mean field equation that we work on. And this particular term corresponds to the effective mean field term. And this term is coming for the beyond mean field term or LHY term, which is negative in 1 dimension and positive in 2 and 3 dimension. And then we have the Rabi coupling and the spin orbit coupling is there. And we are working with the binary species. And here we can tune the number of particles with this normalization in the system. So here what we find that if we consider very low number of particles like a 10, then we have the solitonic kind of behavior of the quantum droplet. As we keep on increasing the number of particles in the system, then we have this sort of bound state or the flat top droplet that we call it. So here one can see that it has some surface tension as kinetic energy decreases very fast here. So it will have the bound state and we have the surface tension. So this kind of ground state we can tune using the number of particles in the system, and beyond certain number of particles, the ground state density doesn't change. So that in that state we say that quantum droplet the kind of behavior starts appearing in the system. Similar the transformation we can do by tuning the beyond mean field term interaction that is governed by delta G. And what we can see here that if we use very high the spin orbit coupling, then instead of having this smooth pattern, we can have this stripe pattern in the system, and that also we can make the droplet like a structure but with a stripe. So with this, we identified using this chemical potential and total energy present in the system that when we can have the transition from the soliton-like droplet to the flat top droplet, or and that will be more closer to the classical droplet. So and then we further studied several of its behavior. Now we basically analyze several of the special cases. First case we consider where we can have zero mean field interaction. So for that we have considered same interspecies is negative of the interspecies interaction, and that makes delta G equal to 0. And that was quite easier to get the analytical solution, and using this the field approximation, we were able to get the sec hyperbolic square nature of the soliton present in the quantum droplet, and that matches quite well with our mean field, beyond mean field simulation, as well as the analytical result and have the quite good matching in both stripe phase as well as the plane wave phase. So with this, we basically analyze some sort of dynamics present in the system, and the main purpose of using the dynamics was to get an idea that whether the state that we are getting, it is a stable one or the unstable one. So for that we give the different sort of perturbation. First we get the ground state, and then we give the velocity perturbation by conserving the momentum of the system. So one component is given velocity in negative direction, other component is given positive direction, and then we have given quench in several coupling parameters, or also we have analyzed the collision dynamics just to understand that whether it has the same feature as the classical droplet or it basically carries the different features. So this is just the velocity perturbation. So here we get that it is a quantum droplet that we have, and then once we give the velocity to it, then we have the breather-like structure, and it breaks into that breather-like structure. And once we give higher velocity, then we have the multiple trains that basically comes into picture. However, if we do the similar thing with the flat top, then what we see that we get the moving multi-soliton without basically changing any, without giving any trap or anything. So with this, we also analyze this collision dynamics. So what we find, just like classical droplet, if we give a very small velocity to both the component, and then it collides at that point, and then it gets scattered to the different direction. So for a small velocity, the collision is inelastic in nature. And for high velocity, the collision is just like a bound state collision, and we get this kind of elastic collision. So with this, we also analyze that what will happen to this droplet when we quench the Rabi coupling and the spin orbit coupling. With the Rabi coupling quenching, we have these several interesting features that basically appears in the system. So here, for what we do, that we start with omega f equal to 1, and then we quench it to final value 4, 11, and 30. So for 4, it remains stable up to this point, and then it breaks into 2 droplet that moves in the opposite direction. And for this one, we get the different branches of the quantum droplet. And here we very interestingly get some solitonic trains that becomes quite, that basically keeps on dividing as it moves further. If you look at this behavior in the real space, then we get the structure of the condensate like this way. So the question arises that how to understand this dynamical feature of the system that we get here. And similar feature we can see if we give the quench in the spin orbit coupling, that basically leads to give some extra motion to this droplet. And it basically shows several complicated behavior that we can capture again through the real space profile. So question arises that how to quantify this sort of instability that we are achieving here by quenching the parameters. So for that, we have performed this Bogoliubov-Dijins analysis, that is just a small plane wave perturbation that we give to the ground state, where this U represent the perturbation amplitude for the right moving plane wave, and this one represent the amplitude for left moving plane wave. As we do that, then we get something like eigenvalue problem, and then we try to find out this eigenenergy, this eigenenergy for this Bogoliubov matrix. And what we get, that if the system is in solitonic state or in the droplet state, then dynamically it is stable. By looking at this imaginary part of this matrix, we get that it remains 0 for all the value of n. So that gives us the hint that it remains stable if we are in this soliton or droplet regime. However, if we basically look at the same thing for high value of the spin orbit coupling, then we see the appearance of this negative part as we increase the n value, and that suggests that stripe part is dynamically unstable. So with this, I just want to conclude the first part of my talk, that here we just analyze using the beyond mean field theory, that what can be the nature of the soliton and droplet dynamics, and we then characterized this at different dynamical feature, and that we complemented through our analytical calculation using Bogoliubov-Dijins analysis. And this work still we are continuing in 2 dimensions, but right now we don't have real to share, but we want to extend the similar kind of thing for 2 dimensions. So before going on the next topic that we basically want to address from the point of view that what will be the turbulent energy cascade for the quantum turbulence. And this work has been done by Savan, is sitting here, a PhD student, and Mohan Verma, Simeon, and Makoto Subota. So here, we basically have in mind that we have the turbulence feature all around in nature. And here we can see the Jupiter, and this is the turbulence behavior in the soap bubbles. So these are 2-dimensional in nature. So one thing we can analyze here, that if you keep on zooming this area, then we find a lot of similar structure. And if you keep on going under keep on zooming, then you find different kind of a structure. So turbulence is nothing but the chaotic behavior in space and time. And due to that, one question arises that how to quantify turbulence. And in classical turbulence, it is quite well known now that one can classify it using the Reynolds number, which is the ratio of nonlinearity present in the system to the viscosity. So here, the famous Reynolds experiment is given, where the flow is laminar, where Reynolds number is low, then we can see very straight flow. And once Reynolds number is quite high, then we see that streak basically gets break into several parts as it moves on, and then we get the chaotic behavior in space and time, and it becomes quite multi-scale in nature. So in turbulence, the story, classical turbulence, the story is 300 years old, and since then people have been trying. And there are a lot of the seminal model or phenomenology to describe the turbulence behavior. People ask the question here in the statistical nature and in the momentum space that how the energy basically get traveled from one momentum scale to the another momentum scale. So here one can assume this high momentum scale as the dissipative scale, and this is the forcing scale. So if one forces this one at this momentum scale, then for very high Reynolds number, this region, which is also known as inertial range, where one can ignore the viscosity and forcing term in the Navier-Stokes equation, one finds that this cascade is power law in nature with exponent minus 5/3. That is known as Kolmogorov scaling. And if you analyze that how the energy basically cascade, or what is the rate of cascade of energy in the momentum space, one can analyze, one can find that this remains constant. So the flux is constant in that inertial range. But similar thing, if one can do in two-dimensional turbulence, then they find that there is an inverse cascade of energy, and due to that we have the formation of big giant vortices that I showed you in the case of soap bubbles and Jupiter. So in that case, we have two sort of cascade. So forward cascade will be above the forcing scale, and this inverse cascade will be below this K value. So we have the existence of both the cascade. So this kind of question, then we ask that what will be this nature in case of quantum turbulence. And Professor Adhikari basically already mentioned this thing that in BEC, we have the vortices that is present as a topological defect that we can generate either by giving the rotation or phase imprinting or several other method, but it is quantized in nature. And since here I am not using any trap, so these vortices have the quantization number, winding number that is equal to 1. So the main motivation of our work comes from this extensive simulation that was performed in the case of quantized vortices, and they consider the different sort of vortices. So like here, the one result is with the Navier-Stokes equation, and then they consider the GP equation and simply consider the initial condition like a discrete vortices which are randomly organized. And then in other cases, the vortices are in disorder in nature. And then they also solved the hydrodynamic corresponding equation for GP equation. So the interesting result was that if the vortices, all the like vortices, like here blue represents, green represent the clockwise, and the other color represent the counterclockwise vortices. So if you zoom this area, you find the different kind of configuration of the vortices. So sometimes the same rotation vortices come together, and sometimes they get mixed. So when they get mixed, that is known as random configuration of the vortices. Once they come together, then it means that they are organized. So when they are organized, then it has been seen that this vortex line decay with a power law T to power minus 3/2, and corresponding energy spectrum will follow the Kolmogorov scaling. However, if the vortex line density decay with this power law, and that has very much quantum effect, then it follows the K to the power minus 1 scaling, and that is known as Winen scaling. So here what we see that there is one arrangement of the vortices that make the cascade just like a classical cascade, and there are one arrangement of vortices that is Winen-like cascade. It makes the cascade the quantum cascade, because that is not observed in the classical case. So here our main aim would be to get this kind of cascade in the context of different ground state of the quantum droplet. And I would convince you that there are several parameters that we can play with, and we can get either classical cascade or quantum cascade or both the coexistence of both the cascade. So with this, here we have this dynamical equation, beyond mean field equation that we solve in the 2 dimension. Right now we are not using any light matter interaction, so spin orbit coupling term is off here. Only we are using the binary species, and with the assumption that the density of both the states are same. So in this particular case, what we basically see that we will solve this set of beyond field equation for the different configuration of the vortices. And how will we generate the vortices? We follow the laboratory experiment where this some sort of steering potential is being used, and that is being and superfluid, that steering potential steer the superfluid, and that generate the vortices. So here I just want to advertise our GPU code that we have developed recently, developed by Savan as a part of his PhD thesis. It is published, and this can perform a wide variety of simulation starting from 1D, 2D, 3D turbulence, and any complex simulation that we can expect. So here I show you the 3D simulation with the quantized vortices. So in this case, what we do that we have the 2 kind of ground state for the condensate. One, this part correspond to the Gaussian potential that we are giving. That's why this the density is minimum here. So we have one droplet which is homogeneous in nature, and other droplet is bound one. So we'll be using these 2 ground state of the condensate, and then we will try to manipulate the energy cascade from classical regime to quantum regime and so on. So here I show you the simulation that this black one corresponds to the Gaussian obstacle, and it basically moves, it gets rotated in the superfluid, and it generates these vortices. The black dots are vortices, so it may be anti-clockwise vortices and clockwise vortices. So in that way, both kind of vortices are being generated, and with this here what we see that we start rotating it, and once we rotate through this superfluid, that generates a lot of acoustic wave. So kind of turbulence that we are dealing here, that also have the sound wave, and that basically makes it compressible turbulence. And after 3 rotation, we remove this obstacle. So here you don't find obstacle, and then we let evolve the system and analyze the decaying turbulence. So with this, what we find that if we use the dipole, if you use the forcing, we generate the dipole nature of the vortex configuration, then there are different part of energy. So this represents the interacting part. The kinetic energy will have the 2 components, incompressible and compressible. So incompressible component will give us a quantitative idea that how many vortices are present in the system, and compressible will give us about the strength of the acoustic wave present in the system. So through this one, what we get an idea that depending upon the kind of vortex configuration that we are using, developing, so dipole means that there is a high chance that clockwise and anti-clockwise will stay together. Random means that they will be random in nature, and clustered means that these 2 kind of vortices will form a giant configuration. So in this case, what we see that this incompressible kinetic energy that remains higher for cluster case and dipole case, but in random case, what we see that it is lower than the compressible part. So the kind of acoustic wave that we are generating, that is higher for the random case. So then for how to characterize the different configuration that we generate through this steering, we use this second order vortex sign correlation. So with this, what we implement that if same kind of vortices are together, then this coefficient will be 1. If the opposite kind of vortices are together, then this correlation will be 0. So then we scan the strength of the Gaussian potential through which we steer the condensate, and this is the velocity. And we scan the whole region, that what kind of vortex configuration we are able to generate through this different parameter regime. The parameter regime here is, this is the strength of the Gaussian potential, and this one is the velocity or the rotation speed through which we create the vortices. So what we see here, we find the different sort of regions. So like this one is one region that basically is simply dominated by the vortex configuration, which are dipole in nature. So we get positive and negative dipole together. Then we have the second region in which it is random in nature, and in the third region where same sign vortices are staying together. So with this, we basically try to see that what will be the nature of this cascade in these three kind of configuration that we have generated in the different parameter regime. So what we see here, that once the vortex configuration is random in nature, then we get Wien-like scaling, and this scaling comes k power minus 3 scaling comes due to the vortex. If it is clustered in nature, then we get Kolmogorov. So using the potential strength and the velocity at which we rotate the obstacle, we can have a control whether the cascade will be quantum in nature, that is Wien-like, or classical in nature, that is Kolmogorov-like. So then we analyze this flux as well, and we generally find that here, although system is 2-dimensional, but it is forward cascade behavior that we get for both the cases. Similarly, we analyze this compressive part of the spectrum, that is generally weak wave turbulence due to the cascade of the acoustic wave at different momentum scale, and that nature comes like k to the power minus 3 by 2 for all the cases. And here for random case, we get some thermalization that I am not going in detail for the sake of time, but it is quite interesting for this random case. And overall, again, we get the forward cascade even for the compressible case. And then we scan through the different parameter regime, where we change the potential strength as well as rotation speed of the obstacle. Also, we change the number of particles in the system, and then we get either Kolmogorov or Wien or mixed scaling throughout the regime. So in that way, we are able to separate the regime where we can get only classical cascade or only quantum cascade or the mixed cascade. So then we analyze the same thing for the bound state of the droplet. And interestingly, so this is, in this case, droplet is bound. So then we are steering it, and very difficult to generate the vortices, you can see, because of incompressible, highly incompressible nature of this ground state of the droplet. And that is very close to the classical droplet. And interestingly, if we analyze the spectrum for this case, we do not get quantum cascade, we get only the Kolmogorov cascade, that is for any set of parameter. So in that way, the claim is that in this ground state can generate only the classical kind of cascade. But once we are using the homogeneous that looks more towards the gaseous state, that generates the either Wien-like, that is quantum in nature, or Kolmogorov-like. So with this, we extended this formalism for the binary case, where we have considered the interspecies interaction as well as intraspecies interaction. These are the beyond mean field term. And here we have used again the box trap and some dissipation just to kill the acoustic wave, because we are more interested to know about the incompressible nature of the energy cascade. So here this one is showing the first component, and this one is showing the second component of system. And this white dot represents the vortex generated in the second component, and here similar way, this white dot will represent the vortex generated in the first component. So here what we find that we can again have the different configuration of the vortices that we can generate for this sort of ground state, where we have the box potential. So we are only looking at this flat top state. For that, we only got the Kolmogorov scaling for the single component. So interestingly, what we find here that unlike this single component, here the interaction can dictate the scaling. So I'll take 1 minute. So as the interaction basically here lies very close to 1, it means that delta G is 0, then we get that this Quanon-like scaling for first component, and this is the Kolmogorov-like scaling for the second component. But as we go away from the delta G very high, then what we get that both the scaling behaves quite differently. So in that way, this gives us another parameter to tune this energy cascade, either to make it the coexistence of both quantum and classical nature of cascade together, or make it different cascade nature. So with this, we have expanded the whole regime, and what we find that in this regime, the first component shows only Vanel-like. In this regime, the second component only shows Kolmogorov-like. So although it is binary droplet, but we get the different cascade nature for the different component. So with this, I just want to conclude the talk that here we have made the small effort in generating a different sort of cascade, classical and quantum, through this new phase of BEC matter, quantum droplet, and it very much depends upon the different ground state, and further works are required to see it for on the 3 dimension that we'll be pursuing. And let me thank all my students. Some has already graduated, some are continuing, and these are my beautiful collaborators through which we have been able to get so many ideas and able to do the beautiful work in our institute in BSc. So thank you all. With this, I'll leave you. This is the turbulence in classical, this is in quantum turbulence.
Thank you, Pankaj, for presenting this very impressive body of work. So I'm sure there are questions.
Hello, sir. Sir, from the density profiles, like how can one confirm that droplet state is formed or not? Like from the first part of your talk, like where you show the density profiles, like how one can confirm that droplet state is formed or not? Like how can one?
Yeah, so if you keep on changing the number of particle, then what you see that the higher density, that will not change. And that is the property of a incompressible classical droplet, that density remains constant.
Okay, density remains constant in space, like
yeah, with a spatial variance.
Okay, so then like what is the microscopic origin of this beyond mean field term, which you included?
Yeah, so this is something to do with the BDG excitation or the excitation that system has. So what happens that it goes to the unstable state. Once I showed you the relation that the delta A is less than 0. So it means that mean field term remains unstable. Then a higher order terms takes over, and that makes it stable.
I mean,
so what will happen that its density keep on sinking. So that will increase the density. So you have the next order term is proportional to NAQ. Right? So that term will become effective.
I mean, mathematically I can see, but like microscopically, if you see, like you have a kinetic energy potential trap plus interaction terms, then this beyond mean field.
There's no potential trap. Without potential trap, you have the boundary state here.
Okay.
Because that's a theory I explained, that there is a cancellation between mean field term in the energy and the beyond mean field term. That basically makes it a stable formation at that particular density.
Okay, thank you.
I have a question. So when you are rotating the obstacle, with time, I saw that the obstacle disappears. Like you.
So we are removing it,
because removing the obstacle.
If you keep on rotating, it generates a lot of acoustic wave, and that will simply disturb the whole dynamic.
So my question is, so that means you're stopping the forcing that is the energy injection is stopped after some time.
Yeah,
after
yeah.
this.
So
So-
this is Gaussian obstacle, so we are just removing it from
Yeah,
the
so my
system.
question is, what happens at transient times, at like very long durations? What happens to your scaling behavior? Does it still maintain the Kolmogorov?
Yeah, so we have seen it for very long time. It maintains Kolmogorov.
So it doesn't go to Vinen after Kolmogorov, like it doesn't transit
No,
to like
no, that's
Okay.
the thing we observe.
That's interesting. So that it maintains that clustering
Yeah,
behavior.
yeah, yeah.
Okay, so that means throughout your box, you will have the Kolmogorov clustering
Yeah,
happening.
yeah.
Okay, thank you.
Number of vortices will change, but clustering will get maintained.
What's the end of your first path? You added a perturbation and then you looked at the Bogoliubov excitation
Yes,
spectrum
yes,
to determine robustness of your phase.
Yeah.
So do you have any idea if like this is a generic feature, or does it depend on the specific kind of perturbation that you used?
No, it's a generally like a low-lying excitation that we are talking about to the BDG. So it's a generic, quite generic feature. Like once you have the excitation in the case of the condensate, that is the phonon-like excitation. So similar kind of excitation that we analyze here for the different sort of ground state. That is not homogeneous, but different sort of ground state.
You very nice talk. For the spin orbit coupling, I mean, you are generating the solitons in the presence of the spin orbit coupling.
Yes.
So can I understand that the spin orbit coupling generates some chirality in the motions of the vortex?
Yes.
Or,
Yes. Yes.
And
Yes.
can,
It gives some velocity, effective velocity in certain direction.
that is only in one direction? That's the idea? Or
That can be in both the directions.
but there is some, and what, so there is the chirality depends by the value, or the direction depends by the value of the spin orbit coupling?
Yes, that will depend on the spin orbit coupling value. So, if it is a small spin orbit coupling, if it is lesser than KL square lesser than Rabi coupling, then we get its plane wave or Gaussian profile. And once it becomes higher than the Rabi coupling, then we get it that strike pattern get generated.
I see. And the effect of the spin orbit, I mean, when you have a different scattering lengths, you can still have a vortex, a soliton.
Yeah.
But you, in the presence of a spin orbit coupling, it becomes more stable, or what is the
So like the one ground state change from another one can happen by tuning the spin orbit coupling. So for higher spin orbit coupling, we get this sort of a stripe. And for a lower one, we get this like a droplet or soliton.
Okay, so for the droplet soliton, we don't need a spin orbit coupling, but
Very weak, very weak, very weak. Yeah.
But is it still necessary?
Yeah.
Is it still necessary?
Not necessary, because that's the thing I have shown, that I can tune those states by changing the number of particles. So I can go from soliton to droplet, flat top droplet only by changing the number of particles. That people have shown for binary droplet also.
Okay, thank you.
There is one more.
More comment.
Yeah.
I think all the models you are using are essentially mean field models. They are different from GP. So people call it extended GP or corrected GP or improved GP.
Yeah.
So, but if you go to Bogoliubov genius or quantum formulation of n particles, that is beyond mean field. So everything is mean field.
Yeah, right now we don't have direct derivation, but Petrov basically showed it for binary case, that he was getting the spectrum same like a BDG spectrum. The term that we are using from the Petrov calculation, that is same like a BDG.
If there are no more questions or comments, then let's thank the speakers once again. And we move to the next.